Yeah, so as I told you, I'm using two books. One book is Franklin Kuo, and one book is Desert and Crew. So this time, whatever slides I am taking, it's copied from this book. Today's slides. So we were talking about something called impedance parameter, or you can say that we are talking about two-port network. So in two-port network, you may have two independent and two dependent sources, right? So when you are writing the impedance parameters or the Z parameters, V1 is equal to Z11 times I1 plus Z12 times I2. V2 is equal to Z21 times I1 plus Z22 times I2, right? If I want to find out Z11, Z11 is nothing but V1 divided by I1, where I2 is equal to 0. Z12 is equal to V1 divided by I2 when I1 equal to 0. Z21 is equal to V2 divided by I1 when I2 equal to 0, and Z22 is equal to V2 by I2 when I1 equal to 0. When we are doing this, if you want to make current sources equal to 0, it's as good as you are making that one as open circuit, right? If you are making these current sources as 0. So such kind of analysis or such kind of Z parameter analysis is for open circuited impedances. We also define following things. Z11 is between 1 prime port, Z12 is between 2 and 2 prime port, Z11 and Z22 are open circuited transfer impedances. Z12 and Z21 relates with voltage to current at the other ports. So Z12 and Z21 are open circuit driving point impedances, right? So this is what we studied, right? So all these things are from basically Kuo. So this is copied from book called Kuo. Whenever new book will come, I'll tell you. Okay. Yeah, any doubt at the back? Okay. So if there is no doubt, one more thing, just it's a revision of what we have done. So you might have any circuit which may have inductor, resistance, capacitor, transformer. Anything is inside. You may have following ports, but if you are analyzing the whole circuit, where internally it's defined by other voltage nodes, you may write down the impedance matrix which we have done last time using the mesh analysis, right? And we have written Y matrix, which is admittance matrix, using nodal analysis. You can do that, but it's different than what we are doing right now. Right now we don't care about what is happening inside V1, V2, V3, V4. We are talking about just this port and this. Like, there has to be two dependent variable and two independent variables, and if you can write down everything in terms of these four things, then things are actually two port network. If you can define it by, of course it's modification of what we are doing here, but it's different analysis because we are only talking about two ports where we are interested in what is happening when I'm having following parameters V1, V2, I1, I2, and this circuit might be the black box. This analysis will be useful when you want to drive one circuit to another circuit, just to know that how much impedance will be offered at the input side or output side, or maybe in between if you are taking somewhere else. So this is how it goes, and that is what we are doing. So one more thing, Z parameter can be drawn using this circuit, which is known as T circuit, because there is a T is seen here, right? So such circuit is T circuit. However, if you are interested in making different circuit than what you have done, which is known as pi circuit, so if I want to do same thing, then what can I do? I can do new circuit where V1 is input, where there are, so unit of this one and unit of this one is volts, right? If I want to add these two quantities, means they have to be in series. If they are in series, what I can say, if this is I1, there is an impedance function which is Z11, and you may have another voltage source whose name is Z12 times I2. I am drawing what is written here. V1 is equal to, if I am looking here, V1 equal to Z11 times I1 plus Z12 times I2. This is a dependent voltage source, or depending on I2. If I want to complete the circuit, other side I am going to see V2, where I am going to have Z22 with the current I2 and another voltage Z21 times I1. This way you can make even pi circuit. This way you can make T circuit. So depending on what circuit you are observing, but at the end of the day you should have the same answer, right? Okay, so in this case, rather than going this way, we can write down two equations. One is V1. Can you help me in writing down this equation? So there are two currents, one is I1 and one is I2. Can you help me in writing these equations? So V1 is equal to, whatever way you are writing, just let me know. With the sign also you have to tell me. Okay, V1 equal to I1 times ZA plus ZB times I1 minus I2. Very good, right? I1 plus I2, because both are in same. Thank you. V2 is equal to I2 times ZC plus ZB I1 plus I2. I can rewrite these equations and I can write down ZA plus ZB times I1 plus ZB times I2, and V2 is equal to ZB plus ZC times, ZB times I1 plus ZB plus ZC times I2, right? This is correct equation. You need to map this equation with what we have written here. So you can find out Z11, Z12, Z21 and Z22 through these equations, right? And you can write down that Z11 is nothing but ZA plus ZB, Z22 is equal to ZB plus ZC, but Z12 and Z21, which are dependent on different side of currents, where you are going to have Z12 and Z21 both equal to ZB, right? You can verify this by the equation also, right? Okay. Here what is happening, this kind of network is known as reciprocal network when Z12 and Z21 are same. You see, Z12 and Z21 both are exactly equal. If this is happening, then you can call this network as reciprocal network, and most passive networks are reciprocal. Still I made some condition. Okay, that condition I'll tell you when it's not going to be in future, because there is something called gyrator we have not studied. So when we are going to study that, I'll tell you how this is not going to be the reciprocal. But most of the passive networks are reciprocal. When I'm saying reciprocal means Z12 and Z21 are exactly equal, right? Okay. Something. Okay. Now this slide is copied from who? Okay. So reference is reference number 2. So there might be like a network and two port network. So network requires analysis for all the ports and internal elements. However, for the two port network, you are only dealing with the ports. You don't deal with all the nodes. And there is something called test bench creation. Do you know what is test bench creation in hierarchical way? Yes or no? Okay. If no, then what exactly we are doing? So generally when you are doing any simulation, we are talking in terms of it's a simulation. And I'm making one circuit which is filter, low pass filter. So there are two ways. One guy has low pass filter is already available. Let's say in MATLAB low pass filter is already available, or you can go to Simulink, you can add the poles and zeros location, and you can keep it in black box. You can give input, you can see the output. There is no need to look at the inside dynamics. There is no need to look at the inside circuit and all. However, when you are going to click this twice, you should go to internal diagram, where you might have this kind of structure, or you might have this kind of structure, or something different than this one, right? It may be anything, right, which is going to give you some poles and zero location. So when you are simulating it, at that time what you are doing, before this you are going to either make mathematical model and then you are simulating this, or you are drawing this circuit. When you are drawing this circuit, whenever you want to draw this circuit, you have to define something called ports. These ports might be input, output, and power supply. So there are three kinds of ports which you may have. So let's assume that this is input port, this is something called ground port, and this is something called output port, whose names are as follows. I want to simulate this, then I'm going to make one layer higher than this one, where I'm going to call this circuit, where if this circuit name is LPF, then in that particular test setup, I'm going to call low pass filter. There will be three things are already available, where they are going to ask, here please connect ground, so I'm going to connect ground. Here I'm going to connect output, where it's asking for some load value, and at the input side you may have function generator. So at this port you may have 50 ohm. This is from outside. So this is called hierarchically test setup, where you are not going into the circuit. If somebody has made it, and there are two kinds of people available in industry. One is called design engineer, and one is called verification engineer. So design engineer does all these things. verification engineer does this thing, right? So that is how it goes. So that is what I want to say, that hierarchically we are at the test bench level, where we are only interested on the port and its dynamics happening with respect to V1, I1, or all the ports voltage and ports current. We don't worry about what is inside. It might be anything. I don't care. So that is what the two port network is. But if you worry about inside network also, it's network. It's network analysis. Okay. So two port definition is already known to us. Two equations which are built up with V1, V2, I1, I2. Okay. Before this, because I got chance to just tell you, if you don't know about amplifier, do you know name of this amplifier? Have you seen this structure, right? Ever in your school? I don't care about whether you studied in previous semester or not. How do you know that it's common base? Look, I haven't written what V1, V2, I prime, 1 prime and 2 prime. I haven't talked about that, right? Okay. So what about this structure? Common emitter. How many are in favor of common emitter? Okay, 2 and 3. Who is raising the hand but telling them? Who are in favor, not in favor of common emitter? Okay, so what is this? Common collector. Okay, how many are in favor of common collector? He might be correct also. Nobody is in favor of common base. Huh? How do you find out? Or you mugged up? Okay, mugged up. Okay, it's by the way common collector. Okay, it's common collector. Okay, so before understanding this, just I'll tell you few things. Okay, I talked about this in my laboratory also. I don't know those who were with me in laboratory. So we have to understand two things. One is called signal, which is fluctuating one, which we want to amplify. There are two kinds of things. One is not fluctuating but DC quantity, not fluctuating, and this we are going to call it as common or the common mode. If you remember, I told this right to you people. So one is common mode and one is signal, right? So when we are doing the analysis, which is AC analysis, which is fluctuating one, we are not going to consider DC, or DC will go to zero. When we are doing DC analysis, all AC sources will go to zero. This is how we are going or working on actually superposition, right? You agree with this? Okay. If you agree with this one, I'm drawing something. Right? I'm drawing few more things that might be. I'm connecting this to a function generator. This is what you have done, right? In your laboratory. Okay. So there are three terminals here in this transistor, right? So at base, so by the way, this is called base, this is called collector, this is called emitter, right? So at base, are you seeing some fluctuating signal or not? Yes or no? Yes, because we are giving function generator as some AC signal. This capacitor is allowing AC, so no problem. So this base has, because of this, at the output there is some AC signal, right? But what is happening here? This is a DC value, minus 5 volt, not fluctuating. So when we are doing this, we are going to consider this one as 0. But note that this 0 is not 0 volt DC, it's equal to 0 volt AC, minus 5 volt. That is the real equation. But for a time being, to understand, we are dropping this, right? Let's keep this one somewhere. So AC is 0, not average. 0. 0 is absolute 0. I am not applying here any AC voltage, right? 0 volt AC and 0 volt DC. So there is no signal, by the way, in both the cases. AC or DC, both are 0. So when I am saying, so here sine omega t, if I am applying here something like sine omega t through a function generator to any place, there is 0 volt DC. If I am applying something from power supply, maybe 5 volt. So 5 volt, this 5 volt is DC, but I am not applying any fluctuating signal whose amplitude is actually 0. Can I write this one? That is what I am saying. So amplitude of AC signal is 0. All the things are actually on paper. However, if you are applying some DC potential, there is a fact that you are going to see something like this. Okay. Okay, but we assume that there is no fluctuation and everything is under your control. There is a nice 5 volt line is seen. Then it's 5 volt plus 0 sine omega t. That is what I am saying. This 0 volt sine omega t is equal to 0 volt AC. Amplitude of sine wave or some fluctuating signal is 0. So this is what I was telling you here, right? No problem, right? Okay, let's keep this circuit somewhere else. Now look at the circuit where now look at this circuit. So are you seeing fluctuating signal here? You are also seeing fluctuating signal because of this, but because of independent DC battery over here, there is no fluctuation. So I am going to remove this. I am going to call this one as ground. If you look at previous circuit and this circuit, previous circuit has ground connected to the emitter terminal of this transistor, and when we are saying or we are measuring anything like V out with respect to this one, V in with respect to this one, and this is new ground because we are doing AC analysis and we want to check the absolute values with respect to AC ground. So this particular node is known as common to all, others are not common. And note that if you are going to do the analysis, this will also go to ground and that will be connected to here. Okay, right now we are not going into detail for that, but this is common. So this configuration is known as common emitter. If you look at here, everything is measured with respect to 0 volt AC, which is connected to base. So this has to be common base, and the third possibility might be this one. So no problem, right? This is common collector. But if you switch this to PNP, this becomes common emitter. Okay, right? Okay, so this is common base if base is connected to some DC potential and rest of the things are AC. Otherwise, no. Otherwise, it might be something else, right? So this was one thing I just wanted to tell you for the amplifier topology, just to understand that. Now there is no doubt, right? What is common collector, common emitter? Okay, I'll make some more circuit. This particular creation is known as MOSFET. This is called gate. This is called drain. And wherever you are seeing some pointing arrow, it's called source. Can you tell me the configuration of such kind of okay, there's one thing I forgot. So there may be three possibility for MOSFET: common gate, common drain, and common source. So which kind of amplifier it is? Common gate, right? Wherever you are seeing DC potential, it's common gate, right? Okay. Now there is one more thing which you should know already, but so those who cannot see what I'm saying, then just let me know. Can you see there are two amplifiers connected back to back? One amplifier is common emitter and one amplifier is common gate. Can you see? Sorry, common source goes to common gate, because this is source, gate, drain, gate, right? Right? Can you see these two? So if you are seeing such kind of structure, there are two back-to-back transistors, right? This kind of structure, or common emitter plus common base, if you are seeing something like this, you should tell that kind of setup as cascode. Okay, this is just for your information. Maybe in future you will use this. Cascode amplifier is good for having good amplification. Okay, right? So cascode is different than cascade. So it's cascading of common source to common gate. So cascade of common source to common gate, or cascade of common emitter to common base, is equal to cascode. Right? Okay, so let's come back to our analysis where we were talking about Z parameter, and I'm going to introduce even a transistor also, so that you can understand how transistor works. But we are going to talk only in terms of mathematics, not in terms of physics. Okay, because we are going through the analysis only. So if you have linear time invariant elements, no independent sources inside this, we understand what is independent sources, right? Earlier what we have drawn, we should have that diagram already available with us. No. Okay, I'll draw again that diagram in that case. Okay, so the diagram where this is Z11 times I1, and at V1 side this is Z12 times I2, right? This is for one side. So can you call this one as independent source or dependent source? Dependent. So this dependent source is allowed here, by the way. Okay. Independent source which are coming from function generator, power supply, those are not allowed, but dependent sources are allowed. Okay, so if there is a transistor, you can model it using Z parameter, Y parameter, and you can keep it here. So this is again what we have done. Just Laplace operator has been added, and that has been kept in the bracket. Now there is a network which has been given to us. This is a T circuit where I can find out Z11, Z12, Z21 and Z22 by applying even this mass analysis, and through that we can write down V1 is equal to SL1 times I1 plus 1 by SC times I1 plus I2, and V2 is equal to SL2 times I2 plus 1 by SC times I1 plus I2, right? And then you can write down this matrix. This matrix is two port. You will always have 2 cross 2 matrix. You will not have more than 2 cross 2 in the case of 2 port network. But if you are writing, let's say, impedance matrix using our technique which we have learned earlier, there will be, so if there are three loops of the current, so then it will be 3 cross 3 matrix, or it will be higher than that. Okay, as we know that T similar to T, we can have such kind of setup also to mimic the 2 port network, where you are going to have Z11, Z12 times I2, Z22 and Z21 times I1. You have to follow, and you have to find out these 4 entries. Okay, now similar to that, Y parameter is also, by the way, any problem in Z parameter, to find out Z parameter, you have to apply this KCL, and through KCL you can write down all the equations. I kept some of the examples also at the end. But do you have any problem in understanding Z parameter? If no problem, then there is something called Y parameter. This is more popular, at least to me. Not others, but all the new people who came in new century after 2000, they are following Y parameter in circuit designing. So if you are a circuit designer, hardcore analog circuit designer, people use Y parameter very frequently. And if you are a communication engineer, you are going to use S parameter. Some more are also there, like communication engineers are also using ABCD parameter is also there. That's why I was feeling happy when it's Y parameter. So Y parameter is similar to Z parameter, where you are going to write down 2 equations, V1 and V2. By the way, this is written this has to be 1 second. Where is the where I kept? Yeah. So Y parameter will have 2 current equations one side, and V1 and V2 will be there. For the same network, you can actually have this Y parameter, where these two are the dependent variables, and V1 and V2 are independent variables. And whatever quantity is coming here, you can redefine them as Y11, Y12, Y21 and Y22. Okay, when you are doing this, Y11 is nothing but I1 divided by V1 when V2 equal to 0. Y12 is equal to I1 divided by V2 when V1 equal to 0, and you can write down about Y21 and Y22 while keeping V1 or V2 as 0. When you are doing this, you are keeping voltages are 0. If you want to keep voltages are 0, you need to short circuit them. So like Z parameter, you are making the currents as open one, and you are calling that analysis open circuited analysis. This circuit will be known as short circuited analysis, right? Because of the fact that V1 or V2 will be 0, right? And you can have Y11, Y21 and all such parameters. Okay, so there might be one illustration. So there are three loops. If you are solving for Z parameter or you are solving for Y parameter, in both the cases you are going to have 2 cross 2 matrix for Z parameter and Y parameter. But if you are not doing this, and if you are doing through KCL KVL technique, which I taught you earlier, you can have 3 cross 3, or here in this case if third one is ground, then it's 2 cross 2, right? So it depends which analysis you are using, and you have to use it wisely. These analyses are the one which are going to be asked in your interview for TI if you are interested. Yeah. So this is what I got input from your seniors. So be expert of these analysis, and the values of these things has to be on your fingertip. Right? You have to practice more and more. So there are lots of questions are available. I'll also give you more problems from these two books, right? So can we write down equations for I1, I2 and I3? So what will be the first loop? V1. So it's 1. So let's call this one as 1 by S only, right? So 1 by S times I1 minus I3. Very good. Plus 1 times I1 plus I2, right? That's all, right? Similarly, you can write down V2 is equal to what you are writing, 1 by S times I2 plus I3 plus 1 times I2 plus I1, right? And so on. You can write down third equation also for third loop, right? 0 is equal to, you have to run this loop and you can write down. Main thing is when you are writing this, you are going to have these three equations. But as we know that we are interested in following things. We want to see what is happening at two ports where there are two quantities V1, V2 and I1, I2. One of them is dependent, one of them is independent. If you are considering I1 and I2 as independent and V1 and V2 as dependent, you are going to have Z parameter. If you are taking in a other way around, you are going to have Y parameter. And then you can find out the values. But for that, you have to remove I3 and you have to write down I3 in terms of I1 and I2, which you can write down, right? You have to replace I3 with I1 and I2. So you can write down, let's say, one equation, I3 is equal to minus 1 by S times I1, plus minus 1 by S I2 divided by 2 1 by S plus 1. If you are feeding this value here, thereafter you can have these equations V1 and V2 in terms of I1 and I2 only, and you can have the Z parameter, right? And those parameters are Z11, Z12 and Z21 and Z22. You will observe that these two will be same. Yeah, so that will be the reciprocal network, right? Okay, it has been asked for, okay, he is designing for Y parameter. So then you have to write down I1 in terms of V1, V2 and I2 in terms of V1, V2. Similarly, you can get y parameter also. Just it's playing with the network or the network equations. Right? Okay. So similar to what we have done for z parameter, we can do it for y parameter also. I1 is equal to y11 times v1, y12 times v2, and I1 is equal to y21 times v1 and y22 times v2. Right? If you have these equations, I can draw the circuit when there are dependent parameters I1 and I2, and voltages available here are V1 and V2. So if I1 is equal to Y11 times V1 plus I12 times Y12 times V2, then both the quantity has to be in series or parallel. Has to be in series or parallel. Hmm. So, so Vaishali, so it will be in series or parallel. Yeah, you're talking same thing, right? To her. So tell me, is it in series or in parallel? Hmm? Series. Okay. So series, how many are in favor of series? Look, if there is a current I, I1 plus I2, if I want to draw the equivalent diagram, I is equal to I1 plus I2, it's only possible when there are two currents going down whose names are I1 and I2. Then I is equal to I1 plus I2 as per KCL. Okay. So now tell me, these two quantity will be in series or parallel? Right? Parallel. So this has to be V1. So if V1 and this resistance value is 1 by Y11. So 1 by Y11 times this one is going to give me this value, right? Y11 times V1, that's the first current in this direction. For other one, there is a current, but it's a dependent current source, which is Y12 times V2. And other side, you are going to have two things, 1 by Y22 and current as Y21 times V1. Right? These two currents are dependent one. So this current is depending on this voltage and this current depending on this voltage. Right? We are doing this for doing something which is for BJT and MOSFET small signal model derivation. Have you learned small signal model? You heard about small signal model? Equivalent. So if there is a BJT, if I want to analyze it, I am not going to write down all the times like IC, that IC, IB, IE, all these things I am not going to write every time. Right? I am going to write down its equivalent model where I am going to have only resistance and capacitance or maybe inductor, because we are expert of maybe the analyzing passive circuits. So if you want to do that, you can actually make the model using two port network. So please pay attention here, because this is not given in any book, this is not copied from any book, this is my analysis. Okay, so that's why it's not copied, it's handwritten. Okay, so this was the thing we have. Now derive the two port equivalent model for bipolar transistor. I want to find out how this BJT will look like if I am drawing the equivalent model. So if you want to write down the equivalent model, you need following things. You need two current equations which are dependent one on voltage. Voltages are different nodes. There are two currents. One is at the input side, it's a IB, output side IC, and there are two nodes VBE and VCE, right? So in total you are going to see something like this. Which is similar to what we have seen for the two-port network. You can replace this with Y parameter, you can replace this with Z parameter, you can replace this with H parameter. H parameter is famous for such thing. In the previous century, all the people who are circuit design in previous century, they used to write down their model in H parameter. But we don't write it down in H parameter, we are writing in Y parameter. So there are some advantage also. Okay. Maybe the derivation of this one we'll talk maybe tomorrow. Okay, it's already time is 4. So do you have any doubt till now in Y and Z parameter? Right, Y is brother of Z, it's just reciprocal.